Thanks everyone for coming. We'll get started. Super excited to have I think our first graph seminar with a speaker back in person post-COVID. So thank you all for coming, and thank you, Russ, for coming. Before we get started, I guess I'll introduce myself. My name is Michael Poza. I'm an assistant professor here. As a quick reminder, previously recorded talks can be found on the YouTube channel and the GRASS website. For those of you on Zoom, we'll have Q&A after the talk, and you can submit your questions there via Zoom, and they'll go to the panel who will sort of route them up onto the stage. And with that, it's my really great pleasure here to introduce Russ Tedrake. Russ is a professor at MIT in electrical engineering and computer science, among some other departments. He's also, I think, vice president of robotics research at Toyota Research Institute. So managing two jobs at once there. And I think the director of the MIT Robotics or C-Cell Robotics.
Complicated.
Something like
All
that.
good.
Russ has won, lots of awards, DARPA Young Faculty Awards, Career Awards, Best Paper Awards, many things. Has done a lot of really fantastic work in locomotion. Ran the MIT DARPA Robotics Challenge team. More lately, work on manipulation, really across the board. And for those who don't know, Russ is my advisor at MIT. I was super thrilled to be there for 6 years, and I'm very happy to have him here today. And that.
Thank you, Michael. Not a bad student to have for a couple of years, right? Yeah, so I'm happy to be here in person. Thank you to those of you that came in person, and I hope that I can write large enough on the board for those of you that are watching over Zoom. So I was saying with Michael and his students this morning, I think I'm just getting older, and I thought I would tell you about one pretty specific thing that I'm pretty excited about right now today. And I want to tell you about this new algorithm, as opposed to telling you a little bit about everything I've done or something like that. So I want to tell you about this algorithm for planning with graphs of convex sets, and I'll build it up. Okay, but this is joint work with Tobia and Jack and Pablo Parrilo. Tobia and Jack happen to be on the faculty market this year. They happen to be some of the smartest and nicest people I've ever worked with, so you should interview them. Okay, so and if you like this talk, it's super good work, and they're on the market. Okay, Pablo's not too bad either, but you can't hire him. We're going to keep him. Okay, so I want to tell you about this work. And the picture is one slide can give you the basic idea here, which is that we've for years known how to solve graph search problems, where you have nodes in a graph, a directed graph, possibly edge lengths. We can find shortest paths on graphs. We can solve all sorts of interesting graph problems. And we'd like to just generalize that a little bit today to be more useful for the robotics applications I've been thinking about. And the extension here is that everywhere where we used to think about visiting a node on the graph just being a point, we're going to say every time you visit a node on the graph, you have to pick one element out of a region. And you'll see, I hope to convince you that this is a pretty interesting way to do some mixed, discrete, continuous optimization. It has some strong tools we can bring in from both the graph theory side and the optimization side. And it turns out to give better formulations for a lot of the problems I've been thinking about for years. So by the end of the talk, I hope you understand that fairly deeply. Let me set it up by, put it in context through the lens of thinking about motion planning or even sample-based motion planning for robotics. Okay, so this is the classic picture that I hope many of you know for the probabilistic roadmap, where I start the algorithm by drawing lots of samples potentially in my configuration space. Each sample then gets connected to its nearby neighbors, as long as there's a collision-free edge between them. And I start by building a potentially dense roadmap of these points and make a graph. Okay, and then at runtime I solve a small graph optimization problem. So I'll get my initial point, my new goal, connect it up to the graph, and I'll solve a small graph optimization problem or graph search problem. Okay, what I'd like to do is have you think about every time there's a point in this picture, I want to blow that up into be a region. Okay, the biggest possible region I can fit inside these between the obstacles. And my claim is that that's going to allow us to do better optimization, where before I was initially stuck to the existing roads on the map, and possibly I can do a local smoothing to improve it. If I blow these things up to regions and I can still use my stronger tools, then I'm going to have room for optimization to do its work. Okay, and I'll be able to have room to implement more dynamic constraints and things like this. So that's a useful picture, I think. Okay, so that goal, as stated, is to try to do global optimization-based planning. I'll do it in the context of robot manipulators, but with dynamic constraints. Okay, that's kind of a big goal. So it includes potentially planning through contact. I'll focus more today on collision-free planning, even though the motivation all came from planning through contact. The story, I think, is best in collision-free planning right now. And asking for true global optimization-based methods. I think one of the risks when I talk about things this way is everybody hears global optimization, and I don't really mean that. What I really mean is using the tools of combinatorial optimization, including the tools for approximation and rounding solutions and other approaches that will scale, I think, nicely. There's maybe a second goal, okay, which is for years I've been worried about the fact that sample-based planning is good at some things that optimization is not quite good at. Trajectory optimization is good at things that sample-based planning aren't good at. There's different tools in combinatorial optimization. There's some absolutely ridiculous tools, really powerful tools in AI stylogical planning, these SAT solvers that can solve enormous problems, right? And they all feel kind of disconnected, okay? And this is not going to be achieved in this talk, but there's a general goal of trying to understand more and more of these connections, and I'll give you a few today. Okay, so what do I mean by collision-free planning that has to take into account dynamic constraints? Now, this is older work from us, and it connects to some, obviously very strong work from Penn, right? So if you want to have a quad rotor flying at high speeds, up with its dynamic limits, through obstacle environments, then you've already been thinking about this type of problem. Vijay and Daniel and the group definitely thought about this kind of problem. One of the tools they brought to bear, in addition to all the differential flatness, was to put that into when you tried to do a global planning around obstacles that ends up getting formulated as a mixed integer quadratic program in that case. Okay, and that of course built on work from John Howe and so on and so forth. Okay, so I want to use kind of a simple example. I want to just maybe remind you or introduce you if you haven't seen that work in a while to the basic formulation they used and that a lot of people use. And we'll just understand when it's good and when it's not so good. And if it's okay, I'm going to do it on the board. So it was my little test, which I decided was a little too small. So for the people that I'm going to try to write bigger than that. Maybe I'll even rewrite that next to it, okay? But hopefully, if you're on Zoom, you can even just click on the picture of me and pin that if you want it to get a little bigger. Okay, so the first formulation we're going to talk about here of trying to do collision-free planning around obstacles. Let me even ignore the dynamic constraints to begin with, and just say I want to find a shortest path defined by a little bit strange of a metric. I'll do a right big here. Okay, I'm going to just I'm going to write a problem here where I want to go from a start to a goal. My start is down there in that picture. My goal is up here in this picture. And I want to find a series of points that drive a path from the start to the goal. Okay, I'm going to define the objective here in terms of summing the squared distance between the different points. Okay, and in the standard model predictive control sense, I have to pick how many points I'm going to optimize over. I'm going to pick capital N points here, and I'm just going to sum the distance between these two. I'm going to do the squared distance for kind of a subtle reason. It's not fundamental. We can do the actual distance if we wanted. The reason, if you care, is that just because if I were to solve in these simple problems with the actual distance, then I would not have a well-defined. I'd have a continuum of solutions, right? I could space the points at any intervals And if I do the squared distance here, that it encourages an evenly spaced intervals along the trajectory, okay? But mostly this is a standard sort of model predictive control trajectory optimization kind of problem. No dynamics, just start at the source, get to the target, okay? Minimize the squared distance. Okay, now if I want to put an obstacle in the middle of it. I've got my start and my goal here. Same formulation, but I need to somehow say, for all n, and maybe even for more than that, maybe I want to care even at the intervals here, I'd like that xn is not intersecting with my x obstacle, right? Or conversely, that xn's are in my free space. So the question becomes, how do you write that constraint? Okay, and there's a lot of interesting things to think about in writing that constraint. Okay, so in this particular case, the way that we could write a big M formulation is very easy to see. I can just say, I've got a half plane here. This is a good region. I've got a half plane here. This is a good region. I've got a half plane here. This is a good region. All of those are linear constraints. As long as at least one of those linear constraints is active, then I'm good to go. Okay, so this linear constraint, you can think of it as, this would just be written by like x0 plus x1 is less than or equal than -1, for instance, would teach me that one. I'm going to write that again a little bigger. Okay. So I have 4 of those potential linear constraints. And I want to say either this one, or this one, or this one, or this one is active. So that's a disjunctive program. You have to do a logical or between your constraints. How do you do it? Okay. One way to do it is to add binary variables. So I'm going to add new decision variables. I'll call my binary variables B, okay? I'm going to have a bunch of them. I'll call the one corresponding to each, to the ith constraint, BI, okay? So I have a binary variable that turns these things on or off. And it's actually very easy to see. So this is the line x0 plus x1 is less than or equal to -1. There's another line over here, which is just x0 plus x1 less than or equal to, let's say 4, okay? Just some number that's sufficiently far away. So if I were to write the constraint as 1 minus bi of n times 5, or more generally, some big number m, okay, then that says when the binary variable is 1, okay, then this constraint is active. When this binary variable is 0, this constraint just moves out of the way up to here, okay, and I'm able to basically effectively turn off that constraint. So if I put additional decision variables bi, and I'm allowed to write something like the b's have to be either 0 or 1 for all I and for all n, okay, then I'm close to where I need to be. The last thing I need is to say that I want to make sure that at least one of them is on. So I'll just say that the sum of those, the easiest way to write that would be for all n, the sum of them is equal to 1, okay? At least one of them is on, that would be exactly one of them is on. Okay, is that a good, sort of a natural way to encode an obstacle and non-convex constraint? I made a little GUI for it, right? So just so you have a sense for how that looks and how that works. So here's the little optimization running. These are the binary variables over time. It tells you which ones are on and off. Okay, and I can solve this, this is at your frame rate is probably the limitation more than anything, right? So I can move the start and end around and just, solve this well. It'll find a globally optimal solution to this, using the squared loss objective. They're evenly spaced points, and it'll avoid the collisions. Please feel free to ask questions at any point. Okay. You can guess I'm going to say that there's some pain points in this formulation, right? If you think about it, the number, as I start adding more obstacles, I'm going to add a lot of different constraints. The expense of solving this grows with the number of binaries. I'm adding a bunch of binaries, one per region, but for every time, okay? And so as you can imagine, as you get lots of obstacles, lots of regions, that gets pretty painful. Okay, so we've done different formulations of this kind of problem. This is Robin's work that followed directly on Vijay Daniel's work, which tried to solve a similar problem, but rather than saying I'm outside this region, which scales in a painful way with the number of faces in your obstacles, we instead said, let's try to find an approximate convex decomposition of the free space. And instead of saying you're outside of these obstacles, let's say you're inside at least one of the free space regions. Is that clear? Okay, and then you can do the same kind of optimizations. This has some additional benefits, as I'll say. You can actually also guarantee that you stay inside in a more natural way, even with higher order splines. So just an alternative formulation of these kind of problems. At the core of that was this ability to do a fast approximate convex decomposition. Robin's algorithm was called Iris to do this. In particular, he wanted to have one that could work even on raw point cloud data, finding big convex free regions, okay? So this works by a series of convex optimizations. It tries to find given some initial guess, it tries to find a polytope around this, around that point, and then find the maximum inscribed ellipse, and then find a new polytope. And these are a series of optimizations that can very quickly, and for at large scale, find big convex regions. Okay, so let me write a slight modification of this formulation now using the idea of trying to be in a region instead of outside that obstacle. In particular, there's a lot of, if you know mixed integer formulations, this is going to look like the convex hull formulation of the problem, okay? And I'm going to write it, there's a handful of ways to write it. I'm going to write it using the language of perspective functions because that's a super nice way to write it, in my opinion. So if I have, so first, what's a perspective function? General idea from optimization, but if I have some set, if I have some convex set, X, I will keep the strict assumptions about boundedness and everything to a minimum, but they're all there in the paper, okay? If I have a convex set in, let's say, 2 dimensions in this example, then it's important to know that you can always construct another set. If this is my X0 and X1, I can add another set. I'll call this Z-axis T. And if I do a non-negative scaling of that convex set, it brings it towards the origin. You see what I'm trying to draw here is that this set can be scaled or shrunk down into the origin. If this set is convex, then this non-negative scaling is also convex. That's the perspective function, okay? And I'll use notation to say that if X, right big here, little, that was my little x, it's now in big on the board, is in X, then I can write X and T are in the scaled version of that set. It's a handy shorthand. Okay, so for my shortest path formulation, a nice way to recast this and write the convex hull, which gives a slightly tighter formulation for this problem, but in general, we'll give the convex hull of the problem. Okay, so if I have my a bounded set with an obstacle in the middle, and I'll make a convex set for this top corner. I can make another convex set for this corner, right? I can decompose the free space using an algorithm like Iris. okay? And I'll add binary variables, again, once per each set and each region. I'll make some additional slack variables, okay? And say that xi bin for all n and for all I are inside that scaling. Okay. And I can add this again as binary, as a mixed integer constraint into my problem. This is a continuous constraint, given that it's a convex constraint. Okay, and this is a binary variable. Okay, so I can add this directly into the optimization problem, and similarly solve the optimization problem, at sort of runtime rates for these small problems, right? And it does all the right things. Okay, now if I write it just like this, as I said, and I just said each element of I is in one of these regions, then I'm allowed to, you'll see I clip the corner there, right? And I avoided that in the big M form by asking for each line segment to be inside a region, to be valid for the constraint, and I can do the same thing here. But these codes are actually very simple. The algorithms work, and I just want to show you that it really is just a few lines of code to do this kind of thing, right? I just make some continuous variables. I will tell you about the relaxation in just a second. My binary variables. I add a few extra variables for my slacks. I forgot to write that the original variables xi are the sum of all the slack variables I. Okay, but you can just read this off. It's actually pretty simple code. Okay, if you do just to get a little bit fancier, which I have in the next cell below, but I'll skip. I can ask for the segments to stay inside this too. It just means that in that case, the regions that I make and hand to my optimizer are not the original regions. They're like the Cartesian product of that with itself. So you need 2 points to live in that set instead of 1 point to live in the set. But that all works too. That's the basic setup. Do people understand the sort of the foundations there? Yeah. Okay. I want to now talk about the limitations of those approaches and how I think we can do something better. Okay. I guess I should say one more good thing about them first, which is that when you do the region version, even when you want to have smooth, piecewise polynomial trajectories, you can write convex constraints saying the entire trajectory stays inside a region, so you don't have to worry about interpolation or clipping corners or things like that. And our videos aren't nearly as fancy as VJ's, but we're going for a little Mission Impossible thing with the red string. Yeah, but it works on real hardware. Okay, we did a version of this even for footstep planning for Atlas, right? So the group was using, that was actually what motivated the problem. We weren't even working on quadrotors at the time. We really just wanted to work on footstep planning for walking robots. And similarly, we would use a perception system that could decompose the world into big convex regions, and then we would run a footstep planning algorithm that would sort of step on those regions. From there, we got more fancy, trying to put more dynamic constraints into the problem. So this is a purely kinematic problem as I've been writing it. Okay, just trying to find elements that stay inside there. But if you start adding additional constraints, saying that my paths can only evolve subject to some dynamic constraints, to some extent you can fit that in, right? So you tend to have to make linear approximations or piecewise McCormick approximations of complementarity constraints, right? But you can push and squeeze and get more and more of that in. So this was just an example of doing it for a little dog robot. Okay. Similarly, even for the aerial phase, we broke the space up into these sort of piecewise regions where you can step, piecewise regions where you could fly through the air. Tobia had gone on to do a lot of nice thinking about these kind of problems. So he's, generalizing it to piecewise affine systems. He's thought very deeply about the best ways to formulate the sort of the piecewise affine model predictive control problem, the tightest constraints you can write, the strongest formulations you can get for the mixed integer problems. And he's also come up with some nice algorithms that allow you to warm start the problems if you wanted to solve them online, using not just warm starting a branch and bound tree, but actually understanding how to carry an entire branch and bound tree into the next solve so you can be very efficient. Okay. But we still weren't happy. Okay. All of these formulations got us started, but they just kind of bleed inefficiency, right? And they're infuriating in a couple of different ways. Okay. First of all, the numbers of integer variables go up fast. Okay. That's always a tell for how long it's going to take to run. It's not the only indicator, of course, but it's a good metric. There's lots of integer variables coming in. But moreover, it feels like there's a false combinatorial complexity that we're introducing to the problem, right? By saying that I'm going to have to make, I've chosen 10 time steps, okay? And I'm going to choose for every time step effectively independently which of those regions it's visiting. That's really the wrong combinatorics of the problem. The right combinatorics feel something like, well, I'm in this region for a while, okay? And then at some point I'm going to come into this region, and then at some point I'll make into this region. There's a much smaller actual problem of going left or right around the tree, right? But we're somehow right, our transcription into that optimal control problem has been very inefficient. The other problem is that even once we write it, the branch and bound algorithm seems to be working very hard. Okay, what do I mean by that? You see lots of deep trees, right? It's doing a lot of work to certify optimality, and it's just doing lots of branching. Okay, a good formulation tends to, sometimes you can solve huge branch and bound problems extremely fast. The good indicator is whether your initial convex relaxation, so the way branch and bound works is that at the beginning, you take all of your binary constraints, you approximate them with just bounding box constraints, you solve that convex relaxation. If that's tight, if it happens that by solving that bounding box problem, all your binary variables ended up as either a 0 or 1, then you're done. And you don't have to do any more search, okay? If they're not 0 or 1, then you start playing games and going down the branch and bound tree. So another strong indicator, in addition to the number of binary variables, is just how tight is the convex relaxation. Huge indicator for performance of these algorithms. And I think somehow our understanding of the algorithms, I would say. Okay, so we were complaining about this. We talked to Pablo a lot. At some point, Pablo asked us the right question. He's like, hold on a second. We know that the LP, for the linear programming formulation of the shortest path problem on the graph is known to be tight. The convex relaxation is binary feasible. You only have to solve the linear program. You don't have to solve a mixed integer program. This is a kind of a known thing in combinatorial optimization. So what he's like, your problems are way harder. I'm not surprised at all that it's not tight, but why exactly is it not tight? Okay, and we're just like, okay, well, let's start comparing and contrasting, seeing exactly which step broke. And we realized I realized that I felt like we were writing the problems down wrong. Okay, so let me just tell you this new formulation here. Using the standard vertices are V, directed edges E, okay. The traditional shortest path problem. I put it on the slide instead of the board here, okay, but it's a very simple optimization. The binary variables in the shortest path problem for a graph go on the edges. I make binary variables that are 1 if this edge is in my shortest path, and 0 if that edge is not in the shortest path. Okay. I have a cost of each edge, which multiplies that. So you can imagine if I sum all of the edges that are in there multiplied by their cost, that's the path length. Okay, that's the objective. I want those, in general, I'd like this to be the binaries to be either 0 or 1. What is known is that you only have to require them to be greater than or equal to 0, and you will get a binary feasible solution. This middle constraint just says that the number of edges that are on going into the node has to equal the number of edges that are on leaving the node. It's a flow constraint. And these deltas, which make it a little less pretty, are because the source only has one going out. You have to add one for the source and remove one for the target. Okay. So that's a beautiful, simple linear program, solves at big scales, gives binary feasible. You don't have to solve the mixed integer problem. So what is the difference between these formulations we're writing and this one that's so good? Okay, and this led to the new formulation, which I think bridges the gap. Okay, so now we're going to think about taking that problem, making it more like this, and getting it more right this time, I think. Okay, so the picture is the graph of convex sets. The additional thing is that for each vertex I, I'm going to pick a convex, I'm going to attach a compact convex set, and every visit to that region, I'm going to choose, one element of that set. Okay, I'm going to allow the edge length to be some convex function of those continuous variables. Okay, this is what becomes the useful language. In fact, we're also going to be able to put constraints, convex constraints on xi, xj pairs along either of the edges. That's how we're going to add dynamics in later. We'll be able to put like x dot equals ax plus bu kind of constraints in there. Okay, and the new shortest path formulation looks a lot like that classic shortest path linear program. Okay, where now we're going to say, every time I visit, I have to pick an element from the set. I'm going to, instead of my constant edge length c, I have a variable edge length that depends on xi and lu, that convex function. Okay, otherwise it's almost identical. I have to avoid, there's a little bit extra work we do just to make sure that we don't have loops. Okay, almost identical, but different than these. Okay, what's important is that you can use this same sort of convex hull reformulation on this version of the problem. You can use the perspective functions on that problem to again rewrite this as a mixed integer convex optimization. Right, as it's written, it looks like it's a non-convex objective. You can lift it with the mixed integer or with the perspective functions into mixed integer. Moreover, you can go through and you can evaluate the convex relaxation of that, but you can make the convex relaxation stronger by looking at properties the integer feasible solutions have, and they would look like redundant constraints for the integer feasible. But if you find additional constraints that must be true for the integer problem, you can add them, and that can make your LP or your convex relaxation tighter. It was super interesting, right? So working with Pablo, carefully on this, right? We came in, we said, look, we've got this new formulation that we worked on, we talked about last week, it's super tight. And he looks at it and he says, wait a second, why is it loose over here? And he's like, basically, he says, anytime a human can come up with a lower bound, the LP should be getting that lower bound too. You missed a constraint, right? And so we started hunting for these missing constraints, right? And sure enough, we now understand, I think, thoroughly, we basically found them all. I think we found all the convex, if you are only going to add a linear polynomial number of constraints, I think we've basically enumerated them all, and we have like the tightest formulation you can hope for in some sense. Okay, so if I go back to this sort of running example, I'm going to do the same sort of decomposition of the space. I do a slightly different one for this problem. It's a little happier if I break it up and I try to say, so in the previous one, I had to be careful not to clip corners. The way I clip corners in this one is I say, when you spend some time in this cell, then please spend some time in the intersection of these two cells before you visit this next cell. But otherwise, it's the same kind of idea. I'm going to use the perspective function on the decomposition of the space, asking transitions from this region to go through the intersection. Okay, but I'm going to write it now with the binaries on the edges, not on the regions. Okay, and that makes all the difference. I'll just solve it so you can see. Okay, so the code is like pretty simple. You basically just, you define your regions, okay? Add a bunch of edges. I've just added this x minus, x squared, basically, the distance, same basic formulation. I call it solve my shortest path on the graph of convex sets, and I get the same kind of results coming out. Okay, so I can move this thing around and it'll solve. That's an interesting case. Oh, I left the convex relaxation on. Stole my own thunder. Okay, so that works. It gives good paths out. One thing that I want you to notice immediately, the number of points there is less than the number of points in the original problem. I did not have to do any explicit statement that it's going to take 10 steps to get me from the start to the goal, right? In the shortest path problem, something better happens. I can, the number of steps is whatever it needs to get to the goal, the shortest path, by that metric, right? So this has always bugged me. The fact that like a PRM or an RRT can make any length path it needs to get to the goal. But if I'm writing a trajectory optimization problem, I've got to pick n equals something and optimize. And maybe I can try to make the last ones go to 0 or something like this, but it's never, I think there's some false symmetries that we're sticking in there. That's Pablo's way to think about it, but there's something wrong, I think, about asking it to get there in a certain amount of time if you don't know exactly, if that's not a hard requirement in the problem. Yes. Awesome. So the question, I've learned to repeat my questions. The question is, isn't that number of time steps coming from the dynamics constraints? So yes, so if you have to say that I'm going to be, xn plus 1 is a of xn plus bu, then that is a natural way to somehow have a time discretization. You can certainly do that. You can make the graph in the Riccati sort of form like that. But I think this is the shortest path without the dynamics in this case, but this begs for a different way to write those dynamic constraints, more like the funnels that we talk about in LQR trees or something like, any reachability sort of computation, I think has to play that role here. Okay, so did that resolve our issues, right? So first of all, I said there was too many integer variables and the transcription added a false combinatorial complexity, right? I love that the path length is no longer predetermined, at least until you add dynamics, we'll talk about that, okay? There are lots of integer variables, but there's not this times n integer variables. There's one integer variable per edge, per transition, depending on what your graph looks like. That could be a lot or not so much, depends how sparse or how dense, but it avoids what I always thought was this plague on having this false combinatorics. The other part is that the branch and bound was working too hard, I said, because of very loose convex relaxations. And this is a super important point, okay? So if I go back to the big M case, okay, so this is my big M case, the first formulation, and I say, run the solver with the convex relaxation. I haven't hit run yet, so let's just look. The cost before was, the true cost of the optimal path was 1.9. Commit that to memory. Okay. It's now 1.7, right? It's lower. But what's key is that the convex relaxation for these problems is the trivial convex relaxation. Always, for all these formulations we've written before, if I take my binary constraints and I relax them, then what I get is the trivial path that goes right through the obstacle, right? Even in the perspective form, if I say you need to be in this region or this region or this region or this region, if you relax that problem, you get the convex hull of that region, but you're going to go right through the obstacle. And you get very loose approximations of the true optimal cost. Okay, that one is actually, I should have made the numbers look more impressively. The gaps can be very big. Okay, the same thing would be true here for the convex hull formulation. Okay, but if I look at now the new graph of convex sets formulation, the optimal cost here was 5. Okay, and you won't be surprised, given that setup, that I think I must have run a different thing. So you see it's tight here, but I don't know why my numbers changed. I must have ran it a different way. But the convex relaxation for this problem is tight. Okay. There's something funny that happens if you get a perfect symmetry. I get it right through the middle there. The primal solution actually looks like it's infeasible because you're not really supposed to read the primal variables out directly. And if the talk had been at 11:30, I would have probably fixed that visualization. But the dual solution shows the optimal. In fact, in the shortest path problem, the dual of the flow constraint has an interpretation as the cost to go. It's actually solving the cost to go, basically, a Dijkstra style algorithm. Okay, and the same is true here, and that's how it gets the cost to be tight. Okay, so just for fun, I asked Tobia, I said, oh, if we can do this kind of a problem, like let's scale it up, right? And so this is, start the goal, convex obstacles, or convex regions through the middle, and it can solve like the maze problem in a second or two on the CPU, right? And that's the convex relaxation, right? It's tight. So it's kind of one thing to go around a single square. I tried to use that just for illustration, but you just couldn't even write that down in the other formulation, okay? And for me, thinking about like, what do I think convex optimization can do, whatever, that's, I like that. It's like, like that doesn't strike me as a convex optimization relaxation that I would think of, right? Now, if you're coming from the graph search community, you'd be like, okay, that's a trivial problem. The graph search of the, through the maze is simple. This is the Euclidean version of that, right? It's actually like a humanoid walking through the path, so it's a harder problem. But I actually agree, it's trivial. It should be trivial. If we connect correctly to the tools from combinatorial optimization, it should be trivial, and that's what's finally happening, I think. That's right. If it was just so if it was just like a cell, and not the continuous variables, then we would know it's tight, and graph search would have solved it, right? And it's because it's doing this extra work, right? And because of that, it becomes this Euclidean shortest path problem. So the call out, it's a well-known problem. When I draw it in 2D, there's well understood properties, right? Finding the shortest path from A to B while avoiding polygonal obstacles. Super well studied, understood problem. There's polynomial time algorithms in 2D. We know it's NP hard in 3D, right? There's things that are known about it, and we're not in conflict. We're not improving really that state of the art. I mean, we're improving it in the sense that we've provided a new polynomial time algorithm, which works even in higher dimensions, and is sometimes tight. We know that it's not always tight, right? It's not breaking any hardness results. We have the hardness results for these problems too, okay? But in practice, it's a very strong approximation algorithm, okay? And the fact that it can consume some of the dynamics types constraints that we want to is exciting to me. A few other sort of comments in that regard, right? So if I take the limit where those regions shrink to points, then it actually comes back to exactly the formulation we get from the shortest path on the graph. So that's sort of a sanity check, and it's known to be tight in that limit. Okay, we definitely know that there are instances of the problem that are NP hard. The proofs that make the reduction are in the case where the regions overlap significantly. Then you can just kind of walk around in the graph arbitrarily. You get a Hamiltonian path problem. And there are also, full disclosure, there are simple problems you can write, and we put them in the paper like this, that look not so different from this, where we have gaps, and they typically involve either cycling or some perfect symmetries that sort of pull you in multiple directions. I think we know when it's tight and when it's not. But for many big problems, it's surprisingly tight. And for me, it's very exciting that we can sort of add piecewise affine dynamic constraints on the pairs. So we went back and looked at the problems we were solving for the humanoid walking before. And this is a render of the decision to make for a humanoid to be walking on this region, this region. Some of them are slippery, some of them are not. But it's just a transcription of one of our interesting sort of problems. That's a trajectory of its center of mass. Okay, we solve these pretty big problems. They used to take a long time to solve. The metric I put here is that the lower bound from the convex relaxation used to be 7%. Now it's 80%. That's a good sign. But in practice, it solves like many orders of magnitude faster than the best formulation. So then Tobia's best formulation, then the best formulation from that one of Stephen Boyd his group wrote. They're non-trivial formulations that are being outperformed by changing the formulation. Okay, and it should be suitable for many graph-based optimization problems, right? So that's funny. I just realized I'm not presenting. that would good, but that was a hidden slide, and I just realized I'm not in presenter mode. I'm in preview mode. Okay. Anyway, so I think it can work for other bipart matching, bipartite matching, other formulations as well. All right. So back to motion planning. We told you, we did this sort of PRM analogy. We now have this version that we can use in the sets. We already had a formulation that worked. We've made the optimization of the integer problem scale much better. There's a few other pieces that sort of have to come into place for it to work for manipulators. And let me just motivate it. I feel like as we're seeing robots get out of the lab and into the world, people are deck size, local startup from outside MIT that is doing food preparation. You talk to the big companies, the small companies. I'm hearing over and over again that our robot's performance is limited by the dynamic constraint, the dynamic limits of the robot, and our ability to plan up to those dynamic limits, right? So this is a Franka Panda in that particular render. The Panda and a lot of robots will just shut off if you hit the limits, right? If you hit a torque limit or a velocity limit, so it powers down. If you're trying to move food stuff for a living and the number of dollars you charge is the number of pieces of salmon you move, and you're afraid of hitting that limit, that's pretty annoying, right? So the standard PRM, there are versions, PRM star that will asymptotically get us to something that could be good for particular queries. But I would say in practice, people are not able to solve that optimization problem up to the limits for these problems. Okay. The other thing that as I was thinking about how I would do it, I was trying to look for some leverage, right? And I think that a lot of these problems, people are solving almost exactly the same optimization problem over and over and over again. Well, let me be more specific. Their initial conditions and their final, I think the PRM model is actually good, right? I think that the initial conditions and the final conditions move, and the actual path is different every time. But the constraints are actually pretty constant in a lot of these problems. Maybe a human has to enter and we can, but I think it's actually a place where we can afford to be in mode where we're going to pre-compute regions, for instance, or any of for pre-computation in order to make fast online optimization. And that's kind of the situation we put ourselves in with this algorithm, right? So to make the full leap, if you want to get trajectories through the graphs of convex sets, we've switched now to B-spline parameterizations instead of the piecewise polynomials. We could have used them before, but they have better advantages in terms of putting velocity and acceleration and other constraints in. Those B-spline parameters have to live in this Cartesian product of the set. The same way I had to have 2 points live in one region in order to guarantee that the straight line segment was inside the region. I'm going to have the entire, for an mth degree B-spline, I need m points to stay inside this region to have the convex Hall property guarantee that I'm going to not have any violations. Okay, I can use linear constraints to connect the segments, and I can use linear constraints for derivative limits, joint velocities, joint accelerations, and the like. There's one more big gotcha, which is that the original Iris algorithm that we used to do the convex decomposition assumed that the obstacles were all convex. So we could solve this, SDP, LP kind of alternation. That's not true in configuration space. All my configuration space regions have these, curvy, shapy things, especially if I'm living with revolute joints and I'm colliding with, polytopes. So we've done some new work to make these regions effectively in C space, which is a combination of what Robbins was doing before in the Iris algorithm, but the check that actually certifies that I'm not colliding with the nonlinear convex regions uses a combination of nonlinear optimization and interval arithmetic. Some of the interval arithmetic tools, I just, you kind of didn't look at them for a while and you come back and they just got so good, right? I mean, computers are fast. So this is, something I believe in enough that we've been really, I spent part of my summer basically writing mature versions of this, trying to get it through code review. It's all in open source now, and it's like, unit tested and you name it. All those little pictures are actually the test coverage I put on the algorithm just to get it in past the code review, right? So that's all in open source, and it should be there to try. The last piece is how do you get the torque constraints or friction constraints? A lot of people really worry about the, I don't want my package to leave my end effector, right? There's some friction limit, okay? And that's real, putting in any end effector constraints. And so for that, we're falling back to the time-tested sort of time-optimal path parameterizations that Moritz introduced, and a number of people have improved dramatically. So this beautiful idea that you can, once you have the path specified, you can rescale your trajectory along the path to a dynamic without, and you could basically take away the nonlinear terms from the multi-body equations. Once you know Q, all the other terms can be written as in a convex form. So this is like, this was sent to me, at 3 a.m. or something like this. So let's see how, I've only barely seen it myself, but here we go. So this is, we thought to show it off, let's get a tight bimanual situation, lots of possible collisions, tough stuff, right? As I said, I only watched this like, see. Good. All right, we're solving pretty big problems. This is the convex relaxation, okay? And I think there's gonna be a lot more to come. Again, we pushed hard in the last 24 hours, and I think I'm pretty optimistic. Hopefully we'll have real robots doing it very soon. Okay, so all that's in Drake. I can't help but plug that. People have told me repeatedly that I haven't advertised Drake enough. So here you go. I advertise in Drake. It's good. I actually think it's exceptional for when it comes to physical simulation. I would put it up against any simulator in terms of if you wanted to do sim to real of complex contact mechanics. That's a simulation of a articulate, Allegro hand interacting with an object, and the physics is just really, really nice with all there's a lot of work. I gave a talk at IROS about the contact model we use there, which is doing a lot of computational geometry to make very stable and robust contact force estimation. I think it's good stuff. Okay, so I wanted to tell you mostly about this one thing, which is a new, strong, mixed integer convex reformulation for shortest path problems over convex regions, right? I think it's got really nice properties. It reduces to the shortest path as the regions become points. It feels like the right formulation in that sense. The problem is certainly NP hard, but because it's got a strong convex relaxation, we get very efficient branch and bound strategies. And oftentimes, actually, the convex relaxations are tight, which means in many situations, like that robot video I just showed, you don't ever have to call a mixed integer solver. You solve the convex relaxation, you do some rounding, you just take the ones that are close to 1 or 0. You typically do it in the dual, not in the primal, okay? But you round the solutions to integer feasible, and you get beautiful trajectories that are approximately optimal out. There's initial applications, in manipulator planning. I think it's for me a new way to be thinking about some of these connections. More generally, I really think we need in robotics. When I made this slide, I was like, oh my gosh, there's no learning. Are people going to leave? We do learning too, I promise. But today was no learning. I think some of the great stuff we see in AI style planning, we have to make more seamless connections to the continuous math we know and love. And this is, for me, a new way to think about it, a new lens to think through those task and motion planning kind of problems. All right. I'll just mention that I've been teaching online now. Zoom converted everybody, but all my stuff is online if anybody is interested in more about manipulation, and I'll end there and take any questions. Yeah. My God, do you have to MC, or are you going to?
So maybe I think I have to say one thing first. All right, just as a reminder for people from Zoom, you can ask your questions that way. Will Yang and Vivek Yankini are going to moderate, but just one I could make, sorry, the announcements for later. I take it back. So we'll do Q&A now if Will and Vivek want to moderate. Question, you can come up to the over here or things like
Great talk, Russ. All your formulation, the Boolean, the combinatorial aspect is essentially a disjunctive Boolean formulation. So 2 questions related to that. Can you encode a heuristic in an MILP solver to exploit that? That's one way.
Yep.
The second question is, can you push your graph of convex sets to have more richer Boolean expressiveness?
Awesome question. So I guess everybody heard that from both because of the mic, so I don't have to repeat the question. Okay, so yes, we're solidly in the land of disjunctive programming. We try to leverage all of the general tools from disjunctive programming in the formulation. There are, I think, specific things that we can do in a case where we have a geometric structure here that might give additional leverage beyond the general disjunctive programming. But I think in the land of disjunctive programming, there are ways to write convex hull reformulations and the like. I think we're using the best of those tools that I understand. Now you said also, can I play with the binary structure, right? In many of these problems, there are still subtle choices to make. For instance, the way I just talked about the B splines, right? So you can often write similar problems, sometimes in a lifted Cartesian product space that has a different binary structure. You can imagine logarithmic binary encodings that talk about the number of visits in one cell, and all these tricks. So the landscape is rich there. I think for me, that falls into the second level of how do you transcribe your path problem into that graph of convex sets. But typically those decisions are made as when you formulate the sets, right? And you lift them up to the higher space. They can describe, for instance, the logarithmic encoding or whatever. I do think there's lots of room to play there. Thank you.
So I'm curious, when you talk about using it for manipulators at the end, when you talk about doing this sort of 2-phase approach of path planning and then time scaling, if your motivation is I want to move this many pieces of food around at a time, like how much of a compromise it is to split into those 2 phases when your dynamic limits are really what's going to, it seems like, guide your path planning in order to move as much food as possible.
Thank you for asking that. That's an awesome question. So let me be super clear. Many of the dynamic limits we can put into the first stage, right in the graph of convex sets. In particular, any derivatives of velocity, of position, we can put in directly. So I can put linear constraints on velocities, accelerations. There's, of course, a gap between an acceleration constraint and a torque constraint. The hope is that that's small, right? So what we're doing in the second stage is really taking into account the manipulator equations, the torque constraints. So if those dominate over the acceleration constraints, then that gap is going to be painful. My sense is that acceleration jerk, maybe even constraints, get you pretty far. Yeah.
Great talk, Russ. I hope you get your second time to talk about pose estimation.
That's right.
But looking at the manipulator lifting the plate, how simple should the dynamic constraints be? I mean, in perception, we get in struggle just having the rotation matrix having a quadratic constraint, right? And we have to write papers about how to do the convex relaxation there. How can it be that in such a complicated problem like lifting, with all the frictions and the torques, etc., that the constraints are easy, or you just didn't present them?
This is a really, really good question. So the reason I'm showing collision free right now is that if you try to start putting regions for every possible face, every possible collision, then things still blow up. You know, and in particular, you know, if the geometry of contact does not present itself with nicely convexly approximated regions, you know, this is where the scaling is still bad. And I also completely agree that the problem should not be hard. So I think there's a couple things to say about that, right? So first of all, we're thinking hard about intuitive physics, model reduction, you know, models. Michael's talking about model reduction in his group too. I mean, I think the notions of approximate information states and the like, and trying to find compressed representations all the way through the contact mechanics, I think is a really important idea. The other thing though is, and to connect to the AI style planning. So in these problems, I think if I have to make the entire graph as step one and then start solving, then that I will never compete with the AI style planners, right? All the planners that, you know, if I'm making solving a graph problem on a map from here to drive from here to Los Angeles or whatever, I don't have to, you know, load the entire world's road atlas first. I just start incrementally planning, right? So I think we have to get more of the incremental and hierarchical planning into this framework in order to sort of bridge that gap, right? So I do think it's reasonable to sort of have a level that decides to pick up the plate, right? And then I think when you get down to the detailed mechanics, we've seen that some gradient methods can get the details right? But this high level strategy of, is my hand below the plate, you know, to the left or the right of the plate, that's where I think this kind of machinery is going to play a big role.
Zoom from VJ, which asks, can you say more about how you optimize with splines through convex sets? It seems like you need to allocate time intervals to each set, but you're able to work around this, and how?
Great question. Okay, so basically you write a canonical time, you know, S is between 0 and 1 for each segment, okay? And then you have a time scaling that enters on the other side of the inequality. You basically can convexify that by, I'm saying this, I guess, VJ is asking a pretty specific question here, but I write each time segment as if it's in a canonical time, and then I can scale it to say that the velocities are less than, I basically scale the velocity constraints. So if I have that my total velocity or my velocity limit is less than 5, and I want to shrink the whole thing, then it's equivalent to scaling my velocity limit, which was a constant. So I can flip the time scaling to the other side of the inequality and keep everything convex. So inside, there's a time rescaling that happens in TOPRA, but I'm even in the graph of convex sets. We do scale time there too in order to achieve what VJ asks.
I'm just wondering, is there any heuristic for the time journey? Because if we have a initial time for the optimization, because we need to add some dynamic constraints. So if we cannot satisfy these constraints, we need to add more times. So I just wondering how to rescan the time.
So we just, so I'll repeat that just since the first part wasn't on the mic, right? So what heuristics are we playing behind the scenes here in order to do the time rescaling, right? So because, so I think it gets maybe to even the initial question, which was, you know, about how painful is it to scale against the torque constraints only in the second step? How big is that gap, right? We do, the time scaling in the front half, I think is just a transcription detail, but it is happening. The second time scaling, the hope is that the work that does is small, right? It's really just if my acceleration limits did not capture the true dynamics and I really did pick something heavy up and I have to adjust accordingly, then a little bit of scaling after the fact can be done with this time optimal parameterization. But we're really not trying to lean very heavily on that. I would love to get more and more of the optimization of those constraints over into the graph of convex sets. And I think there's ways to do it where we can use pre-computation to get more and more, of those constraints as convex approximations of those constraints. I'm not sure if that's exactly what you were asking, but I hope that I don't want to overemphasize the time parameterization. I think that's a detail in some sense. Yeah. Okay. Of course, yeah.
This is kind of following up into other questions. You showed this walking example where it looked like there are multiple dots, right? And I saw this in the paper as well, sort of this idea of having to add multiplicity to vertices. How does that mesh with this idea of not having to sort of enumerate per time step?
Okay. Two different, so in the case where you actually have a finite horizon problem, then you can make, I would take my graph here, and I could just copy that graph, once per time step. I could just make one of these regions, at time 0 and copy the whole graph. The same edges that would here, I can restore the Riccati structure. The deeper part of so you can do that. And that's what we did in the humanoid problem, okay? The deeper question that you asked, I think you're asking is that, do you have to do that for the to put in linear dynamics, right? I think if you're trying to obey discrete, difference equation dynamics, then you have to do that. I don't know a way to not do that. When you get into the game of approximating time with Lyapunov functions, reachability analysis, I think that's the way to lift that out. But we're still making all those connections.
You have a nice mixed integer Tedrake computation problem. The Tedrake computation is that element.
Yes, so if in the rolled out version, it's just a better way to solve the problems we were already solving before, but you would still have a fixed number of time steps. It would have tighter relaxations and faster solves.
Thank Russ one more time. And please tune in next week. So Friday, November 5th, same time at 10:30 for our next speaker, who will be Ryan Benjamin from University of Pittsburgh.
Yeah, sorry, there was no pose estimation, but yeah, I appreciate your comments.
When you saw the robots doing this, it seems that we are overthinking the pose. But it's not the case. If you check the correspondence or the outlier selection that